You did homework?
Sure. All right. Turn on the microphone. Something now, hopefully. That's the first time I've had to see that one. So here we go. Let's see. Just 2 days left in class, realistically here. We've got. I think that what we'll do is we'll set aside Thursday as a quiz/review day. So we'll come in for the very last quiz, which will cover this last bit of material on Bode plots and resonant circuits. And we'll do that first thing in the class, and then if you want to stay for any extra review stuff, we can certainly do that. We'll see how much of the material that we get through in the next couple of class periods, because we do have a pretty decent amount of material left. I think we might be able to cover it in 2 days, but we'll see. There is a very, very brief homework assignment that I posted last night. It's just 5 questions covering the main stuff. Man, you guys, whiny. And just covers the very basics of the material that from this chapter. So a simple transfer function kind of thing, although it's just a driving point impedance. There's a 1 or 2 Bode plots, and then a couple of resonant circuit things, and that's about it. So it shouldn't take you very long. I'll get the solutions posted for homework number whatever it was, the last one that you turned in yesterday. Get that posted later today so that you have that to study for. And then for those of you who are on campus, on the screen behind me are the 3 things that you should remember for the quiz later today. That the complex power S is calculated by multiplying the phasor voltage, RMS voltage, times the complex conjugate of the RMS current phasor. Bear that in mind. Also that the magnitude of S, the magnitude of the phasor of the complex power, you take the magnitude of the real power and divide it by the power factor. That's just essentially some trigonometry. And then also a little bit of trig, that the power factor angle theta is given as the inverse cosine of the power factor itself. So if you can remember those 3 things, you can do well enough on the quiz later today. Question?
The quiz is not going to be like a whole this is how much power your thing is consuming. This is your power factor. This is what you want your power factor to be, and then solve for whatever.
No, it's not a power factor correction. It's just calculate the entire complex power of a system. So it should be pretty straightforward. It's basically just like one of the questions that we did in class as some examples, just with different numbers. So if you're going to do some last minute studying, you can look at those and be happy with that. So I'll get I've started looking at the final exam. I think I'll try to have that done in the next couple of days so that I can speak intelligently about what's going to be on it. And for the online students who are going to be taking it early for whatever reason. So yeah, any questions on anything at this point? Okay, so Bode plots. We started talking about them yesterday. Trying to get a handle on how to do these things fairly simply. And what they are in general are just a quick and dirty back of the envelope way of visualizing the frequency response of a given circuit, or frequency response of a transfer function specifically. And because we're going to be working with at least a semi-log plot where frequency is dealt with in a logarithmic way, we can use the property that the if you multiply things, if you have a multiplication of a log, you can separate that out as the addition of those logarithms, and division, it can be dealt with as subtraction. So we can deal with all of the various components, all of the poles, the zeros, and the I guess the constant portion of our transfer function. We can deal with all of those things separately and pull them together at the end, and that's about where we got to. So we can do that in this piecewise fashion, combine all of the influences together and turn it into a full-blown frequency response. We looked at how to do real first-order poles and zeros. These are fairly straightforward. We take and we try to put it into some sort of constant form where, or a consistent kind of canonical form, if you will, where we kind of get rid of that S term again and put it back into the j omega form. And then we try to get it into this area where we've got Z1 separated out. So you have a 1 plus j omega over your pole and zero frequencies. And that means that this constant k, which had been just itself, turns into this somewhat larger deal here, where you've got k times z1 plus, or over the pole frequencies and so on. So that will just keep getting bigger for the number of poles and zeros that you have. And then we looked at, so if we, primarily what we're going to be more interested in is going to be this magnitude characteristic. We'll look very briefly at the phase characteristics, but really we're most interested in the magnitude. And that's what we're going to do. We're going to put that up onto the, into a Bode plot. And we're going to do this 20 log 10 thing, 20 log base 10, to make the addition and subtraction, or the multiplication division, turn into addition and subtraction. And it makes it so that we can do this in the way that we kind of want to, by breaking it up into these separate parts, seeing how each component would behave, and then combining the response. So then we look at each one of the poles and zeros in the constant term, and for the constant term, the value of 20 log base 10 of the constant is just a constant term over all the frequencies, and so it's just going to kind of give you a place where you start at. After that, you look at, when you're looking at the zeros of the function, basically what happens is that for all of the frequencies up to a specific corner frequency, the influence of that term is going to be negligible, and we're going to call it 0 for the purposes of our Bode plot estimation. For larger values, once you get past that corner frequency or break frequency, it basically just increases linearly with a slope of 20 dB per decade, 20 decibels per decade. And that corner frequency is the zero frequency itself. And so it ends up being something where you're going across, you get to the zero frequency, and then it starts increasing in just a nice linear fashion. Poles, on the other hand, they work very much the same way. Their influence up to the pole frequency is 0, and then once you get to the pole frequency, it decreases at 20 dB per decade. So this was our little example where I think they threw in a couple of numbers for exactly, for example, what K0 was. But we looked at all of the different influences here. We have the influence from K0 in red, that's just frequency independent. We've got the 0, which is up until its corner frequency, it has an influence of 0, and then comes up like this linearly. We've got then we've got two different poles. One of them is at 0, the pole frequency is 0, and so it immediately starts decreasing at a negative 20 dB per decade slope. And then the final one has a corner frequency out at something like 5 radians per second. Its influence is 0 out until that corner frequency, and then it goes down. Now as we start we just start combining these things, and we start looking and say, all right, up to, when we start at 0, we see two different there's two different contributing factors. One of them is the constant term 0, or the constant term K0, and the other one is this negative 20 dB per decade slope in blue. Those are our two contributing factors up until, this about 0.2-ish radians per second, whatever this area is here. And so we start out at a specific level at 20 log base 10 of K0, which is the value up here, and we start decreasing because the decrease from the 0 is going to start kind of dominating and pushing things down. So our final, I guess, version of the Bode plot, it starts out decreasing at 20 dB per decade until it gets to this point where we reach the corner frequency of our 0. Then the positive 20 dB per decade slope of the 0 and the negative 20 dB per decade slope of the pole cancel each other out. And you'll have a constant value for a certain period of time until the next corner frequency from another pole or another 0. And so it just goes nice and flat for a while until we get to the corner frequency down here for our second pole. At that point, we've got the green 0 influence and the blue pole influence are already canceling each other out. We've got a nice constant flat value, and then you've got an extra negative 20 dB per decade coming from the second pole, which starts driving this downward at negative 20 dB per decade. So that's how you can put those things together. And we'll do some more example to make sure that this feels somewhat comfortable. Phase plotting is, I'm going to kind of zoom past this because I'm not going to really ever ask you to do phase plotting because it's just not quite as interesting. But just for the record, it's actually somewhat easier to do phase plotting than magnitude plotting. And magnitude plotting really isn't that hard once you start giving it a try. The phase associated with your constant term is 0 degrees. We've already kind of talked about that idea. The phase associated with a 0 is positive 90 degrees, and the phase associated with a pole is negative 90 degrees. And those are all constant values, and so the same kind of thing occurs where you will have these conflicting or compounding influences from your poles and zeros. The transition of what happens as new poles and zeros start to influence the circuit or the behavior of the transfer function, those get a little bit more difficult to kind of look at and deal with. So the specifics here are if you have a frequency that's less than 1/10 of the corner frequency, where the corner frequency again is the pole or the 0 frequency, the phase is 0 degrees. At 10 times the corner frequency, then that phase moves to the full positive or negative 90 degrees. And between the two frequencies, specifically at 1/10 the corner frequency, it goes through 0 degrees, at 45 degrees at the corner frequency itself, and then 90 degrees at 10 times the corner frequency. So it's this kind of piecewise as it makes it switch. And here's what the example looks like, the same transfer function. So there's a constant influence from the K0 term going across here. And then there's two decreasing terms for the two zeros. And so we have this kind of odd phase characteristic overall where you've got the 0 comes up here starting at 1/10 of the corner frequency. It starts transitioning. It goes through 45 at the corner frequency itself, and then at 10 times the corner frequency it's up at 90. And that's what happens for for the zero of the function. The same kind of thing happens for the poles of the function. It goes out for a certain period of time, drops or starts transitioning at 1/10 of the corner frequency, goes through negative 45 at the corner frequency, and then at 10 times the corner frequency comes down and hits negative 90 degrees. We already had a negative 90 degrees down here, and that was from the first pole, the pole with the corner frequency of 0 degrees, or 0 radians per second. So those are the three parts that are contributing to the phase characteristic of this particular response. When you combine them all together, what you get is it starts out at 90, and then because of the influence of the 0 in the numerator, it drives it up towards 0 degrees, but it doesn't get all the way there for two reasons. Well, because the influence of the second pole starts to take over, and it spends a little bit of time flat before it starts driving back down towards 90 degrees. And that would be your overall phase plot. Again, I'm not going to mess around with phase plots a lot. What's more interesting is the magnitude plot. But that's how you can do the phase plots. It is entirely possible, and perhaps in your application entirely necessary, to be more complicated and accurate than what we're doing here. But for the most part, what this will give you is enough information to make sure that the circuit kind of behaves the way that you want it to, or the transfer function is doing what you expect it to do. So let's do a couple of quick examples so that maybe you're feeling a little bit more comfortable with the idea of what these Bode plots look like. Get caught up in my notes here. All right, so really all I'm going to be concerned about here is the magnitude characteristic for this transfer function. This is something that is, totally made up just to get you thinking about what's going on here. And essentially, the first thing that I guess we should be doing to some extent is putting this into, well, this is actually already out of its easiest form, or it's out of the canonical form and into a form that's a little bit easier to deal with, because it makes it very straightforward and easy to see what are the zero frequencies or the zero and the pole frequencies. And so the zero and the pole frequencies for this one happen to be that there's a zero frequency at 2 radians per second. There's a pole frequency at 10 radians per second, and there's another pole at 100 radians per second. That's going to be the overall characteristic, and so you're going to see out of this particular, the behavior for this Bode plot should look pretty similar to the one that we just had, because there are 2 pole frequencies in a single zero frequency. The other thing that we need to establish is what is our value of K0. What we're going to do here is that one way of calculating this in a kind of an easy way is to say, all right, well, we start out with 10 to the 4th, which was our K value in the function in the first place. Then multiply it by each of the pole and zero things. So you have the 0 at 2, the pole at 10, and the pole at 100. And when you figure all that out, that is 20. So that's one way of calculating K0. I'll show you a slightly different way in a minute, but it comes with a slightly different form of the transfer function. So here's what the transfer, or there, these are really all the information that you need, and I will try to use all of the colors here. I don't know how well it'll come out, but so our magnitude characteristic, we don't have anything that's happening at 0 except for the constant term. So let's draw it like this. So this is our logarithmic axis for omega, the radiant frequency. This is the magnitude in decibels. And so the contribution from the constant K0 term is going to be whatever the value of 20 log base 10 of 20 is. And I think 20 log of 20 is around 26 roughly. And the contribution of that constant K0 term is just going to be that constant flat value going across. The contribution of the 0 term, which is in this green color if it comes across, it will be 0 until its corner frequency of 2 radians per second. So at 2, it's going to start increasing linearly at 20 dB per decade. Then in the red color, we're going to do the first pole, P1, which is going to have a contribution of 0 until it hits its corner frequency of 10 radians per second, at which point it's going to start decreasing at negative 20 dB per decade. And then in black, if you can tell much of the difference between these colors. The pole number 2 is going to be at 0 until it gets out to its corner frequency, which is going to be 100 radians per second. Then it's also going to be decreasing at negative 20 dB per decade. So we can put this all together, and I will do that kind of in black on the right. So again, this is the magnitude of H in decibels. This is the frequencies. And so what it's going to start out at is for the first, from 0 up to 2 radians per second, it's going to be flat at that value of about 26, or whatever, however exact you want to get about the value of 20 times log of 20. Then at the corner frequency of 2, it's going to start increasing linearly upwards with a positive slope of 20 dB per decade. So at 2 radians per second, it's going to start increasing upwards, 20 dB per decade. Then at 10 radians per second, that's when pole number 1 starts to influence the behavior of the circuit, and the negative 20 dB per decade of pole 1 and the positive of the 0 will kind of cancel each other out for a while, and the magnitude characteristic will flatten off until we hit 100 radians per second, at which point the influence of the green and the red, the 0 and pole 1, which have been kind of canceling each other out, we'll see that all that's left is the negative 20 dB per decade influence from pole number 2, which will start driving this down at negative 20 dB per decade. And eventually this will drive down to 0 and go into, negative and whatnot. But for the most part, this is kind of enough to get you started. Does that make sense, the way that we put these parts together? We have you just kind of work your way across the graph. from 0 up until 2, the only influence that we see is the constant influence. And so that's where we're going to start. Once we get over to 10, once we get to 2, we start seeing there's a combination of the influence of the constant term and the positive. At 10, we see the positive 0 and the pole slopes canceling each other out. When we get over to 100, we see that we've got another negative slope driving down. And so this, I don't know what kind of circuit you might call this if you were going to try to call it some sort of filter. Because what you would see in kind of a neat filter magnitude characteristic might be a Bode plot that looked something like this, where there's nothing, kind of goes up and then comes back down, and that's a classic band pass filter. It's saying that for certain frequencies, I'm not going to let anything through. For other much higher frequencies, I'm also not going to let anything through. But for some frequency range in the middle, I want that to go ahead and come through. And so, that's the kind of thing that you'll start seeing with these transfer functions. Here's another somewhat more complicated and hopefully interesting example. Which also brings into account another interesting behavior of a Bode plot. So here is our transfer function is 20 times 0.1 j omega plus 1 over j omega times j omega plus 1 and 0.01 j omega plus 1. So there's our transfer function, and it's more in that kind of canonical form. So if we want to find out where the corner frequencies and stuff are, we need to do a little bit of very simple math to make that happen. So we'll start by getting all of these fractions away from, fractional coefficients away from the j omega terms. And so pulling this 1/10 out of here, see if I can make sure I get this right. We pull that out, and that's going to make this make it j omega plus 10 as our numerator term. Then we'll have j omega, we don't have to do anything to that. We've got j omega plus 1, also don't have to do anything to that. And then we're going to pull the 1/100th out of the third pole, and so that'll be j omega plus 100. And so now it's really clear what all of our pole and zero frequencies are. We've got a pole with a corner frequency of 0. We've got a pole with a corner frequency of 1, a pole with a corner frequency of 100, and we've got a 0 with a corner frequency of 10. The one thing that I kind of deliberately left off is what is the value of k0. And in this case, we started out with 20 as our value of k, and then we pulled out 1/10 from here, and so we're going to divide by 10, or essentially multiplying by 1/10. And then out of the denominator, we pulled 100th. So that's divided by 1 over 100. And so when you run all of that math, you get 2 divided by 1 over 100. That just becomes 2 times 100. And so our value for k0 is going to be 200. So that's our value for k0. And I apologize kind of for the mess up here. To some extent, this math makes me uncomfortable because I know that this kind of process works. This procedure works for doing it, but I'm not comfortable with the way that the math happens when you start pulling these numbers out, but kind of how it works. So let's put down some of our things. We got our value of K0 as 200. Our zero frequency that we have is at 10 radians per second. Pole 1 is at 0 radians per second. Pole 2 is at 1 radian per second. And pole 3 is at 100 radians per second. So we can graph all of these little bits and pieces at do each one of them one at a time and then start combining the influences, or you can try as much as possible to just start kind of dealing with it as you go. So here's omega. This is again the magnitude of h and as a decibel plot. But we can kind of try to do it on the fly too. So we see that initially we're going to have two influences. We're going to have the constant influence, and we're going to have the influence of the pole 1. And so the original kind of top value is going to be 20 log base 10 of 200, which is about 46. So our Bode plot's going to start up here at about 46 decibels. And then the pole influence with the corner frequency of 0 radians per second is going to take over more or less instantly. And we're going to start decreasing at negative 20 dB per decade. Until we get to 1 radian per second. And this is where something, we haven't seen this exactly yet. But now we've got two pole influences. This one is decreasing at 20 dB per decade. This one is also decreasing at 20 dB per decade. And so their cumulative influence is negative 40 dB per decade. And so you're going to see a slightly steeper but linear slope going down at negative 40 dB per decade. At least until you get to 10 radians per second, at which point it will flatten back off a little bit. So this is, I apologize for the kind of unlinear nature of that segment, but at that point you will have the first two poles contributing a total of negative 40 dB per decade, and the 0 will be contributing its positive 20 dB per decade, which leaves you with a total of negative 20 dB per decade. And so it still continues to decrease, but slower than it was before. And so it kind of flattens back out a little bit more at just negative 20 dB per decade. And that starts at the corner frequency 10. That will continue out for a while until you get to 100 radians per second, at which point it will start decreasing again at negative 40 dB per decade, starting at there, so negative 40 dB per decade. So that's that's at least one relatively simple Bode plot. And we've got some more examples that I can do. I think they're all, yeah?
Is there anything when it goes below 0? Is there any difference between it being at 0 or?
There are occasionally when we're doing more advanced Bode plots, and I don't even know that there are any of these necessarily in our textbook this time, but you do start paying attention to what the magnitude characteristic looks like as it drops below the x-axis and goes into negative magnitude stuff. And sometimes they're concerned even with where does it cross the 0 axis of and getting into negative decibels. So, yeah.
Negative going down at negative 20 dB, right? Why did it go shift back up to negative 20 after going down to 40 and not going down to 60?
At 10, it makes the shift back up to negative 20 dB per decade because at 10 radians per second, we have three competing influences. We have the negative 20 of the pole at 0. We've got negative 20 at the pole at 1 radian per second, and we've got the positive 20 of the 0 at 10 radians per second. And so it starts out from 0 to 1 at negative 20. At 1, we have got both of these, and so that becomes negative 40. And then once we get out to 10, we've got all three of these influences. Negative 20 plus negative 20 plus positive 20 just gives us a negative 20 overall. And then once we get down to 100 radians per second, we've got a total of negative 60 and positive 20, which gives us a negative 40, which gives us the cross. And so just to be clear, this actually crosses the 0 axis somewhat earlier than this diagram would suggest. And it crosses somewhere between 1 and 10 radians per second is specifically where it crosses that and gets down into negative magnitude. So we've got, let's see, why don't you guys try this one real quick? I've got an extra example here. So here's a transfer function. 100 over j omega times 0.1. Why do I keep closing that? J omega plus 1. So there's the transfer function. So what does the Bode plot look like? And the first thing to do is to turn that into its easier form to figure out where those poles and 0 frequencies are at and what the new value of K0 is. So what is this kind of easier form of the the transfer function look like? What is the value down here in the denominator at least? Yeah, this is 10. So what is the value of K0?
1,000.
We pulled a 10 out of here. That was in the denominator, so you had 100 divided by 1 over 10, or 1,000. So do we have any zero frequencies? No zeros. We've got two full pole frequencies. What are the pole frequencies?
0 and 0.
0 and 10. Okay, so where do we start out in our, what's the initial magnitude of the function? 60? That's, it's not,
And 1,000.
20 log. That is the way that I would have done it, and that is not the answer on the in the solution manual, which isn't at all consistent with yeah. And that's what I get, and so I would be curious to, they say 40, and my concern is that they didn't do it quite.
They didn't add the extra 10 underneath them because log base is at 182
Yeah.
times 20 would be 40.
I'll have to check on that, because I don't, to see if they've maybe fixed that or something, or changed their minds on it. But, because that's what I would have said the answer was. So we start out at 60, and what are we doing from there?
Bring it down.
Yeah, we start decreasing at negative 20 dB per decade, as influenced by pole 1. Then what happens? At 10 radians per second, we start decreasing even faster at negative 40 dB per decade. And that will just keep going down ostensibly forever. So that's a tremendously simple Bode plot, but it's a Bode plot for you to hopefully feel maybe just a little bit more comfortable about doing that. So one of the things that we mentioned is that those were all simple poles, real and simple poles. But not all of our transfer functions have that form. Some of them have complex poles, because we could have terms in the denominator that are quadratic. You can have a s plus or j omega plus something squared. The whole quantity is squared. And so if you have those quadratic roots of your function, you might find that they're real, or you might find that they're complex. And it really doesn't matter if you do have repeated real roots, because we can deal with that. You'll just end up with a negative 20 dB per decade slope for each one of those pole functions, or a positive for the zeros. So what we need to figure out is what to do when you have complex poles, when you have a j root on your function. So this is what the kind of really nasty form looks like. You have s, which is is replacing the j omega term, plus some real component alpha, plus minus j beta, or again, this is just, you've done your factoring and tried to figure out what are the roots of the quadratic form that's on the in the denominator or whatever. And we can do some stuff to kind of play around with the form of the denominator to try to get it into something that isn't quite so ugly. So we rewrite that as s plus alpha quantity squared plus beta squared. which is once you FOIL that out, you have s squared plus 2 alpha s plus alpha squared plus beta squared. Rewrite that again, replacing the idea of 2 alpha, replacing alpha with zeta times omega n, and alpha squared plus beta squared is also equal to omega n, or alpha squared plus beta squared equals omega n squared. And so does that look at all familiar? It should look at least something like the equation that we had for second order parallel RLC circuits, or I guess both second order serial and parallel RLC circuits, where you have s squared plus, let's change the color here, s squared plus 2 zeta omega naught squared, or times s times omega n squared. And one of the advantages to being more consistent in using Irwin's description of all this stuff is that you do see that you get more used to using this zeta term. But it doesn't really affect us, I think, a ton. But it's got the same kind of form, because in what we called the radiant resonant frequency way back, we called it the resonant frequency back then. It's the same kind of idea here with the complex poles. So the final form of the equation, once we've done all of our substitutions and rewriting stuff, is that the final form is 1 minus omega squared over omega naught squared, omega n squared, plus j times 2 times zeta times omega over omega n. So we've got this pretty nasty coefficient on the imaginary term. And the value for k0 is just k over omega n squared. What does that all mean? How does it actually affect us? Well, what it kind of boils down to is that complex poles and zeros, what they do is they cause amplitude or magnitude changes at positive or 40 net. Let's try this one last time. The magnitude characteristic changes for a quadratic term at positive or negative 40 dB per decade, just kind of as a rule of, that's what they do. And then the corner frequency is a little bit more difficult. You have to kind of separate things out enough to figure out what omega n is. And that will tell you where the corner frequency is. The phase, I mean, you can look at all of this stuff, but number one, I think on the homework and on any quizzes or anything, the final exam, I wouldn't put, I didn't put anything phase related anyways, but secondly, I don't think that I put, I don't remember now if I put a quadratic term on there or not, but it's something that essentially what we're most interested in is the magnitude characteristic anyways. And so, but you see that the phase does a very complicated transition based on, I don't know where this number 4.81 comes from, but it seems very specific, but also very random. So, but the key thing, quadratic terms change at positive or negative 40 dB per decade, and the corner frequency is this omega n that we can solve for. So we can, just as a quick example of doing one of these magnitude characteristics for a complex or pole. Boy, there's just not a lot of information on this this slide. So the magnitude characteristic that we're interested in here is h of j omega equals 100, 0.02 j omega plus 1 over j omega squared. What is clear is that, boy, there's just not enough information on this. I don't like this example. I'll have to come back and kind of look at this example some more. But the complex pole in the denominator causes us to have a negative 20 dB or negative 40 dB per decade slope. Though when we pull out the 0.02 here, 0.02 is 1 over 50. So that means that at 50, we're going to change from, we know that we'll change from a negative 40 dB per decade slope to a negative 20 dB per decade slope, because we get the zero at 50 radians per second. The one thing that, man, I apologize for this example because it kind of stinks. What I can tell you right now, without going back and double checking all of this stuff, is that we have a negative 40 dB per decade slope from the quadratic term. And I do not have an initial magnitude for you, and all it says in my notes, helpfully, is that k0 equals k divided by omega n squared. But looking back up at this, it's difficult. I'm thinking that the frequency for omega n must be 1, either that or it's 0. But I need to check on that to find out exactly what this is, because I can't remember how to solve this one. What I do remember is that at 50 it changes to a negative 20 dB per decade slope. And it crosses the 0 axis at so apparently what is n? So that's the magnitude characteristic. We'll come back to this one tomorrow, and I will have more information for you, because I'm not at all feeling comfortable on this one. So it's been a while since I've attacked this one. So we will come back to this and do better on that one. So that you should be able to do the easier Bode plots on the homework, as well as I think the driving point impedance one. So we'll come back and I will have more information for you on how to do this one properly. Then we should be able to get into resonant circuits for a little bit, and hopefully kind of finish this stuff off tomorrow. So aside from wondering why I even came to this class today, do you guys have any questions for me before we do the playlist? All right. Again, we'll try to finish this stuff up tomorrow. If you do have any questions, try to ask them sooner rather than later, and we'll see you tomorrow.